So, all right. So I'm going to be talking about some of the interpretation of these models, and basically, a lot of people like to refer to neural networks as black box model. We don't know what's going on, and we don't know what's going on. We just know that it does good prediction of what's going on, of labels. So we wanted to really open that black box and understand why the neural network is assigning important, or what is going on inside that black box. And so, in order to do that, let's quickly review some of the ecology of glioma. So, glioma is this. It's almost a synonym for brain tumor. It's a common brain tumor, and it's a brain tumor of the glial cells. And generally speaking, there are features that are known to be important to brain tumor and have been known for quite a while. Uh, so IDH mutations, and it's actually one of the big discoveries in cancer biology in general, are these mutations that affect C mutations, histone modifications, basically the alterations of the DNA transcription. But they're also one of the earliest examples of cellular metabolism being affected by a mutation, and cellular metabolism being a key player in this. Um, Other important mutations known for progression of gliomas mutations, and so I just want to focus your attention on IDX mutations, on the fact that chromosomal alterations such as 10q loss of velocity, or 1p or 19q, for instance, it's not shown here, but these are also chromosomes that are important. So chromosomes are these basic DNA material which is wrapped into what we call chromosomes. These are basically the macrostructures. Um, so you really can see these chromosomal alterations on the image, like, and also point your attention that cell cycle, so things related to how quickly the cell divides, are related to glioma progression. Unsurprisingly, things like CDNA and other cell cycles. So in 2015, there was Emory led this effort. And as a matter of fact, he, our advisor, and Dan Brad, leaders in brain ML, he led this effort in basically classifying gliomas. And it was actually the first time the World Health Organization decided to incorporate genomics in the grading of any tumor in general. So it was a real breakthrough. And basically, what they found out is that when you use genomics, um, hopefully also with some support from histology, you actually get a better stratification of patients than if you use histology. And you can see why here. So here's an astrocytoma. Here's another astrocytoma. These guys, they live for maybe 6 years. These guys live for 1 year. They look exactly the same on the microscope. But by looking at IDH mutations, you can really distinguish them in terms of survival. By looking at the correlation, you can distinguish things that we can see under histology. So you also get the stratification that you get in histology, but with additional stratification. So anyway, so 2 years ago, this was the paradigm shift in how we think about gliomas in terms of genomics and histology combined. And I want to just turn your attention that when IDH is wild type, so um, people usually think of mutation as associated with worse survival, but as a matter of fact, IDH is associated with better survival for reasons not related to. So IDH, when IDH is wild type, these astrocytomas tend to behave similar to glioblastomas, and many of them will turn into glioblastomas. Glioblastoma is a synonym for grade 4 astrocytoma, basically astrocytomas that are required dead cells. So let's look at survival. So as Safoora mentioned, we get these patient-specific risk profiles for individuals. And we have two models. We have an integrated model that has other all sorts of biological factors, and a transcriptional model that looks at individual. Um, so what would you expect? Or you would expect that what we found and incorporated into both of the organization models should look up as otherwise. And that's exactly what we get. We get what we expect, and later we actually can do some knowledge discovery too. So not just confirming discovery. So let's focus on these categories, graded data sets in different data types. So let's stratify. So this is the top 10. The reason you see box plots is unlike linear models, like Safoora mentioned, our models get for each feature there is a different risk depending on what patient you're looking at. So really personalized. And each dot is one patient and their risk for that specific. So you can see age pops in the top 10, chromosomal alterations, glioblastomas. So these are all kind of expected. You see epigenetic alterations, so you see IDs talking about lower risk, i.e. better survival. Um, and you see smart alterations related to epigenetic changes in the cell, changes to cell signaling molecules and mutations, and you see chromosomal. And then, just further, like Kaplan-Meier curves, we show the Kaplan-Meier curves that these really stratify the patients longer ones who live shorter times. So Kaplan-Meier here, basically, as time progresses, what proportion of the patient population survives. So the higher the curve, the more the patient survives, the lower the curve. Um, so the other model we looked at is the transcription. So the transcriptional model is the expression model, which genes are active, which genes are not active, and so on. And we, instead of looking at individual genes, well, 20,000 of them, we decided, let's be realistic and look at patterns, how these genes interact with each other, what's their so this is how we interpret biological models. Um, and for people who are not familiar with expression, this is like molecular circuits. So these are circuits or direct graphical models. Nodes and edges and direct edges or whatever. Um, so these technical gene set enrichment analysis, which is fairly standard, is basically higher the enrichment score, higher the enrichment score, the more likely you are to encounter members of that pathway at the top of the grid. High enrichment score means more members of the pathway present at the beginning of the system. So here's one paradigm that we learned. We got a lot of expected pathways, but one thing we thought was interesting to show is that EGF beta and executive transition both show pathways. So red, this is the risk score for this person, red is 5%. And these are some components of the beta pathways lining up. And the same goes for executive. And from basic biology, we know that TGF is one of those pathways in cell signaling and inflammation, other things. But one of the nice connections is really TGF beta is the key cell signal pathway regulating EMT. And I said that both of them do so light up in our genes, which means that somehow in glioma biology, EMT regulated through